let's continue with hypothesis testing. We'll define a couple more terms, but we'll just do a bunch more examples. Remember, the purpose of a hypothesis testing is to determine whether we should reject or fail to reject the status quo, i.e. the accepted value of the population mean. And really what we're doing is we're seeing whether there's enough evidence to reject the null hypothesis H naught or not. Okay, so you can pause and read example 1. What are the appropriate null and alternate hypotheses? Well, the appropriate null hypothesis is that mu equals 69.4 inches, which is the height, mu being the average height of older men. The alternate hypothesis is that mu is less than 69.4 inches. Now, how did I get that? Well, it says less than, so I'm getting less than. And where am I getting 69.4? I'm getting it from right here. Okay. So now that we have that out of the way, let's compute our test statistic, which remember is our z-score, right? So our z-score is going to equal, remember, it's our sample statistic minus mu all over our standard error, which is really just sigma divided by root n. So this is going to be 69.0 minus 69.4 all over 2.84 divided by the square root of 300. Now, if you ever wrote this down on an exam or something like that, like on a quiz, I would give you full credit. But it is good to, get an actual value. So, let's put our stuff into Excel and see what we get. So we go ahead and we put in, 69.0, population standard deviation is 2.84, sample size is 300, and the hypothesized mean was 69.4, right? So that gives us a test statistic of negative 2.4395, okay? So let's go ahead and screenshot that. I'll just stick this down here. Some evidence. Right, so our test statistic is negative 2.4395. And where are we getting that from? We're getting it from right here. Okay. So what's the conclusion now? Well, since our p-value is really small, we reject the null hypothesis and conclude men in their 60s are shorter on average than the average man. Okay, that's our conclusion. All right, and I refer to this as HA. I really should refer to it as H1. Okay. So note that the alternate hypothesis stated that the height for older men was less than 69.4. That should have been 69.4 inches. And when it states that mu is actually less than the accepted value for the null hypothesis, our hypothesis test is called a left-tailed test. And of course, if the alternate hypothesis states that mu is greater than the value in h naught, then we have a right-tailed test. Okay. And so again, you can use a chart to find them, but to find p-values, but I'm always going to use Excel. Okay. So can you go ahead and pause, read example 2. Let's do the problem. What are the hypotheses? What are the hypotheses? Well, null hypothesis is going to be that the mean weight that the scale gives out is 1,000 pounds. The alternate hypothesis, well, you have to read that a little bit more. But again, I think we see that word differs from 1,000, right? Differs from 1,000. So it's going to be that the mean does not equal 1,000 pounds. Even though we got a sample mean that was a bit bigger, our alternate hypothesis is that it does not equal 1,000 pounds. Because we just care that the scale is off. We don't care whether it's too low or too high. Okay? So those are our hypotheses. Now to compute our test statistic, we're going to say z, which again we know equals, you don't have to write this, I'm just doing this for illustrative purposes. This is going to be 1,000.6 minus 1,000 all over 2 divided by the square root of 50. And what does that equal? I have no idea. We're gonna put it to Excel, find out, right? Let's do it. We get 1,000.6. We get 250. And our hypothesized mean was 1,000. So you see there's our test statistic right there. Get at this. And so we get our test statistic of 2.12. I just say 2.12. I guess 1.3. Why not, right? And again, where are we getting that from? We're getting it from right here. Okay. There's our test statistic. Now, for alpha is 0.05. Note that since, again, we're looking at this guy. Well, I guess let me stick with using red as the, there, right? So I'll say, since p equals 0.0339, which is less than 0.05, reject the null hypothesis. And what are we going to conclude? We're going to conclude the scale, the scale is off. And gives a weight measurement different from 1,000 pounds. Maybe I should say on average. Okay. Now, note that in this alternate hypothesis, right, we stated that the mean scale weight differed from 1,000 grams. Is that 1,000 grams? Oh, no. I kept saying pounds. Well, let's change that. Sorry. It was grams. Grams. When it does that, when it just says differs, then our hypothesis test is a two-tailed test. Okay? Now, just a couple things to emphasize, a couple of terms I want to define, a couple of concepts I want to define. When we reject the null hypothesis, we're not saying for certain that the null hypothesis is incorrect. Rather, we are saying, and this language might look familiar, we know with, I guess I'll say, 100 times 1 minus alpha % confidence that the null hypothesis is incorrect. Okay? So even though the evidence very well might be on our side, there is a chance that the null hypothesis is, in fact, correct, and we were incorrect to reject it. This is really bad. The error of rejecting a true null hypothesis is a type 1 error. And it's never good to make an error, but this is a bad error because we are rejecting the status quo. We are making people question what has been established. And it turns out we were wrong to do so. So we really want to avoid that. We want to avoid rejecting a null hypothesis that's correct. Now, the probability of a type 1 error occurring in a hypothesis test is alpha. The significance level, right? Notice that it's 1 minus the confidence level, right? So the idea is that in, for example, a left-tailed test, the idea is that if this is mean, if this is mu, and this is x bar, and maybe this right here is alpha, or I shouldn't say that that's alpha. Sorry, I lied. I shouldn't have said that that was alpha. But this value right here equals p. And if it turns out that p is less than alpha, then we reject the null hypothesis. Right. But there is still a chance that we were wrong to do so. Right? And that's for a left-tailed test, by the way, okay? Now, analogously, there are times where we fail to reject the null hypothesis. And again, we are definitely not saying that the null hypothesis is correct, but rather we're saying we just don't have the very strong evidence required to reject the null hypothesis. Right? The analogy that the book gives is it's like finding someone guilty. There's a very strong burden of proof to find someone guilty because you can't make the mistake of sending an innocent person to jail, right? It's better to to find someone not guilty when they're really guilty than to find them guilty when they're really not guilty, okay? So even if the evidence is on our side, there's a chance that the null hypothesis is, in fact, incorrect. And that we were incorrect to fail to reject it. The error of failing to reject the null hypothesis when it is, in fact, false is called a type 2 error. And the probability of that occurring is something called beta. We're not going to get into it. You can look in the book. It's a little complicated. but it's related to, it's 1 minus the power of a test. And anyway, let's do one more example. Okay, we've got this guy. We've got hypotheses. We've got n, got mean, sigma. Compute the value of the test statistic. So z, well, what's z going to equal? It's going to be 12 minus 14 over 6 root 48. And let's see what that winds up giving us. Bust out Excel. 12. Oh, 6. 48. Hypothesis mean was that 14, I want to say. So our test statistic was negative 2.03. Note that, by the way, I did not adjust the significance level, right? I just kept it at 0.1 because I can draw my own conclusion. But maybe you should, feel free to change the significance level, okay? Anyway, we're getting negative 2.3094. Okay, again, where am I getting that from? Right here. Okay. Do we reject the null hypothesis at the 0.05 level? Well, let's see. If it's not equal to, since p equals 0.0209, which is less than alpha equals 0.05, yes, reject the null hypothesis. But since p equals 0.0209 is greater than alpha equals 0.01, no, fail to reject the null hypothesis. And that's what we've got.